So the COM, or we can call it as a one complement. Okay, so this instruction performs a one complement of a register. So this is what the operation do. Okay, which is to perform a one complement. Okay, you can simply press the calculator by inserting this formula here, which is FF minus RD. RD is the content of your general purpose register. So this is the syntax. So COM RD, in which RD can be from R0 to R31. Okay, for example, let's look at the example. Okay, we have R17 equal to 74, for example. Okay, so now inside of the R70, you have a 74, and then you're going to do the COM R17. So what? Okay, so by using this operation here, okay, you have a calculator. Okay, you go to your calculator and press FF minus RD. So what would be the result? FF minus RD, FF minus RD, your RD is 74. Okay, then you will get R17 equal to 8B. This is after you execute the COM R70 instruction. So now we are going to check whether this value is correct or not. Okay, so what you're going to do? Okay, since this is a first complement, okay, you have the 74. Okay, by convert this 74 hexadecimal to binary, you will get 0, 1, 1, 1 and 0, 1, 0, 0. Okay, so this is a 74. And then how to change this binary number to first complement? How to what are the result after you change this binary representation to first complement? What you're going to do?
Okay, invert all.
Okay, so you need to do inverting. Okay, means that zero, 0 will become 1 and 1 will become 0. So this one you get 1, 1, 0, 1, and this is a 0, 0, 0, 1. Okay, and then you change back this binary representation to hexadecimal, then you will get 8. Okay, so it's 8, 4, 2, 1. 8, 4, 2, 1. So 8 plus 2 is 10, 10 plus 1 is 11. 11 change in hexadecimal, you will get B. So you get the same answers. Okay, so this is the COM. Okay, so every time you see the COM instruction means that you're going to do the first complement. Okay, next we have the NEG. Okay, so NEG stand for two complements. Okay, you're going to change the value to second complement. So NEG instruction replace the content of register RD with its two complement. So this is the operation, okay, in which 0, 0 minus with whatever value inside your RD and put back the result in the RD. So this is the syntax NEG RD, and your RD can be from R0 to R31. Okay, so let's look at example. So we have the R16 equal to B3, for example. Okay, and then you suddenly you run an instruction NEG R16. Okay, so this is the initial value of your R16, which is your R16 have B3, and then you run the NEG R16. So now what happened to R16? What is the value that you will get? Okay, you can simply press your calculator by key in 0, 0 minus with RD is B3. Then you will get, what is the value you get here? What is the result show in your calculator? Anyone? Okay, you get F, 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 F for D. Okay, so now, since R16, okay, what is the size of R16? How many bits of R16 your GPR?
8-bit.
Okay, so R16, your GPR is only 8 bits. But this number here, okay, you see here, how many bits this number have? 1, 2, 3, 4. Okay, you have a 4 bytes. So 4 bytes, total 32 bit. Okay, you have a 32 bits. Okay, this number have a 32 bits. So since the R60 only 8 bits, so what you're going to do? You just take the lower byte and put it to your R16. So R16, the value of your R16 after you execute NEG R16 is 4D. Okay, then we're going to check whether the answer is correct or not. Okay, so what you're going to do? Okay, you have a B3, change it to binary numbers. Okay, so B, what is B? 11. 11 is 1011. And then 3 is 0011. Okay, then how to change to this number here, this binary value to second complement. How to do that?
Add 1 to the significant bit.
Okay, you have two, what we call here, two method here. Okay, the first method is the longer one lah. Okay, in which the first step, you need to invert the value, okay, to first complement. After you inverted the value to first complement, then you need to add with 1 to get the second complement. Okay, the shortest one is you're going to traverse, okay, from right to left. Okay, from right to left, you find the first one. Okay, so this is your first one. So what are you going to do? You copy back the numbers. And what about the rest? The rest you just inverting all of them. Okay, so now this one, since this is a 1, so it becomes 0. And this is a 1, 1, 0, 0, 1, 0. Okay, and then you change back to hexadecimal. So this one is 4, and this is 8 plus 4 is 12. 12 plus 1 is 13. 13 is A, B, C, D. So you get 4D, which is same with the formula. Okay, the one that you press, the one that you get from the calculator. Okay, and then, okay, for this one here, okay, you can see what are the flag affected every time you do the NEG. Okay, so there are a few flag affected here, which is half carry, sign, overflow, zero flags, negative, and carry flags. Okay, so that one is for the NEG, which is you're going to do the second complement. Okay, then we have another instruction called SBR. So the SBR stand for set bit in register. Mean that, okay, so this instruction set a specific bit in a register RD, which is you are going to perform the logical ORI. Okay, it is a similar with the ORI, which is the SBR is actually similar to ORI instruction between content of the register RD and constant value and place the result in the destination register RD. So this is the operation. RD equal to RD do logical OR with a K. K is your immediate value. Okay, so this is the syntax. SBR equal to RDK. RD can be from R16 to R31, while K is from 0 to 255. Okay, for example here, the current value of R17 is okay 11000000. So this is the initial value of R17, sorry. Okay, so by looking at these bits here, okay, so now you based on this value here, bit 7 and bit 6 are high while the rest of the bit is 0. So now what you're going to do is, okay, you're going to set bit 3 and bit 2 so that, okay, so bit 3 and bit 2 you're going to set so that the output would be 1100, okay, 1100, okay. Initially, you have bit 7 and 6 set, and now what you're going to do is you're going to set the bit 3 and bit 2 as well. So the bit 7 and bit 6, the value, the other bits will remain lah. Okay, so now what you're going to do, okay, so we're going to use the SBR instruction, which is we're going to set a specific bit in the R7 register. Okay, so we just use the SBR. So this is the instruction SBR, and what is the destination register? R17. Now what are the value that we're going to put in this K here? Okay, so the K here is depend on the value that you're going to put here lah. Okay, so since we are going to set bit 3 and bit 2, so bit 3 and bit 2 we put 1, while the rest of the bit we'll just put 0. Okay, so this one here you change to hexadecimal and it will give you, okay, 0, 8 plus 4 is 12, 12 A, B, C, so 0, C. Okay, so this is the instruction that you're going to do in order to get this output here. Okay, in which, okay, previously you only have bit 7 and bit 6 set, but now not only bit 7 and bit 6 set, now you're going to set the bit 3 and bit 2 as well. Okay, so this is what the SBR do. Okay, and another example. Okay, so this one. Okay, you're going to set 4 MSB in R17. Okay, let's say lah your R17, the current value of R17 is 0, 0, 0, 0, 0, 0, 0, 0. Okay, so now what you're going to do is you're going to set this 4 MSB bits. Okay, while the rest of the bits you need to put 0. So how to do that? Okay, so you just use the SBR instruction. SBR, what register that you're going to set? R17. And what value that you're going to put here? 0x F0. Okay, then the output of R70 will be 1111 0, 0, 0, 0 after you do this operation. Okay, and then this is the flag affected, which is S, V, N, and Z, and you see here the V always 0. And how about the CPU cycle? Okay, it only takes 1 clock cycle to execute the SBR instruction. Okay, so just to inform you, okay, this slide here are already uploaded in the e-learning. Okay, you can download them from the e-learning. Okay, for this lecture slide. Okay, then we have the CBR. Okay, CBR is a clear bit in a register. Okay, previously we're going to set a certain bit inside of a register. Now we're going to clear a certain bit or a specific bit in a register. So the CPI instruction clears specific bits in a register, which is it perform the logical AND. Okay, so this is similar to the logical AND between content of the register and constant value and place the result in the destination register. So this is the operation. Okay, you see here, RD and with FF minus with K. Okay, so this is the syntax CBR RDK, which is your RD must be from R16 to R31, while K is from 0 to 255. Okay, we look at example. Okay, R20 have this value. Okay, so now what you're going to do here is you're going to clear the odd bits. Okay, clear odd bits. Okay, so 0, 1, 2, 3, 4, 5, 6, 7. Okay, so now you're going to clear. Okay, so this is the expected output. So this is the expected output, which is you're going to clear the odd bit. All the odd bit will be clear. Okay, while the rest, the even bit will remain. Okay, so okay, so now you write the instruction CBR R20. So now we are going to find out what is the value that we're going to put here. Okay, so since you're going to clear the odd bits, okay, what you're going to do here is you need to put one to the bits that you're going to clear. Okay, since this one here, we're going to clear the odd bits, which is bit 1, bit 3, bit 5, and bit 7. So we just put one, okay, to this bit, while the rest of the bit, okay, you put 0. So this is the value that you're going to put here, which is OX A. Okay, so now let's check whether we get the same output or not by using the CBR instruction. Okay, now we're going to apply this formula here. Okay, the operation here, which is RD dot with FF minus K. Okay, so you have a FF minus with AA. So what would be the jawapan here, the result? Okay, FF minus AA. Okay, you will get 55. Okay, so you get 5. Okay, then this 5 here, you're going, okay, so this is a 5. Now you're going to end with your RD, R20. So what is the R20 value, the initial value of R20? FF. So you have a FF. This is your FF. This is the initial value of your R20. Okay, and then you're going to end with 5. Okay, 0, 1, 0, 1, 0, 1, 0, 1. And you do the logical AND here, then what you get, 1, 1, and with 1 you get 1, 1, 0 is 0, 1, 1 is 1, this is a 0, 1, 0, 1, 0. Okay, see, you get the same answers. Okay, so this is the result after you perform the CBR R20 OX AA. Okay, so any question up until here? Okay, so this is the flag that affected every time you do the CBR, which is you have a sign flag affected, V flag overflow always 0, and Z. Okay, while the rest of the flag will remain. Okay, next we are going to see the SER. Okay, so SER stand for set all bit in register. So SER instruction load FF directly to the register RD. Okay, so this is the operation you see here. You put FF to your RD. Okay, so this is the syntax SER RD, and RD must be from R16 to R31 only. Okay, for example, you're going to set R17, okay, you're going to put with FF. So how to do that? Okay, you have two solutions here. Okay, one by using the SER R17. Two, you can do the LDI R17 with OXFF. Okay, you can do either of this instruction. Okay, so actually the SER means that you're going to set all the bit in that register with 1. So what happened here after you execute this line? So R17 will have value FF. Okay, so for the SER, okay, there are none flag affected every time you execute this instruction here. Okay, and then we have the CLR. Okay, so CLR stand for clear register. Okay, previously you set all the register value, and now you're going to clear this register value. So how to clear the register value? Okay, to clear the instruction, this clear instruction, CLR instruction clear a register. Okay, so it will perform an exclusive OR between a register. It says, so this is the operation. RD do exclusive OR with RD, and you put the value in the RD. So this is the syntax CLR RD. For example, you're going to clear your R20 with 0. So how to do that? Okay, again, you have two method or two instructions to do that. One, you by using the CLR R20, okay, or you can simply load I R20 with 0. Okay, so these two instructions do the same thing, which is you're going to clear R20 with 0. Okay, so there is flag affected, okay, for the CLR, okay, which is sign flag will be 0, overflow is a 0, negative is 0, while the Z flag always 1. Okay, why is Z flag always 1? Because the content inside of R20 is 0. So that's why the Z always 1. Okay, then we have the TST. Okay, so this TST stands for 0 or minus. Okay, so this TST instruction tests if a register is 0 or negative. Perform a logical AND between a register. It says, okay, so this one here, you're going to check your flag register. Okay, which is the flag register that you're going to check either N and Z. Okay, so this is the operation. RD do the logical AND with RD and put back the result to RD. So the syntax is TSTRD. Okay, and then we have the swap. Okay, so this is a swap nibble, stand for swap nibble. Okay, swap instruction, swap high and low nibble in a register. Okay, so this is the operation here. You see bit 3 to bit 0 will go to the bit 7 and bit 4, while bit 7 and bit 4 will go to bit 3 and bit 0. So this is instruction swap RD, which is your RD can be from R0 to R31. For example, okay, R30 now have an initial value of FA. Okay, then you do the S swap R30. So what happened to your R30? Okay, so here, what happened here is A will go to location position F, while F will go to position A. So the output will be, okay, the result will be A, F. So this is what the swap do. Okay, which is you're going to swap the high and low neighbor in a register. Okay, and the last one here is an NOP. So NOP stand for no operation. Okay, so this instruction perform a single cycle, no operation. Means that just going to waste some time. Okay, if you're going to waste the time, then you use the NOP instruction. How many times that it will be wasted? Only one CPU cycle. Okay, and then so let's look at the exercise. Okay, any question up until here? Okay, we have already finished the data processing. Okay, which is in data processing, we already cover the arithmetic instruction as well as the logical instruction. Okay, for the data processing, we have another two type of instruction, which is data shifting and data flow. Okay, that one we will be looking at in the next chapter. Okay, and any question up until here? Okay, if no question, so let's look at this exercise. All right, so now, okay, the first exercise here, okay, the first example lah, okay. So you are going to write a program, okay, to add two 60-bit number. Okay, so you're going to add two 16-bit number, which is the number is 2762. Okay, and then you're going to add with 1296. Okay, and then it says that place the result in R26 and R27, in which the R26 should have the lower byte. Okay, so what happened here, after you do this addition of 60-bit number, you're going to put the result in R26 and R27. Okay, so now you're going to write the program, okay, to perform this 60-bit addition. So how to do that? What are you going to do?
We separate, doctor. We separate the number.
Okay, so first, you need to divide this 16-bit number to 8-bit number, which is you divide them, all right, to lower byte and higher byte. Okay, for the lower byte, what instruction that we're going to use in order to do addition process?
LDI.
Hmm?
LDI.
No.
Add
So
with
now,
carry.
okay, now we're going to do the addition. Okay, for the lower byte, what instruction that we're going to use? Because for the addition, we have the ADD instruction, and then you have an ADC instruction, and another one is ADIW. So what instruction that you're going to use for the lower addition here?
The first one, the first instruction, ADD.
Okay, we're going to use the ADD. Okay, what about the higher byte? What instruction that you're going to use here to add the higher value here?
ADC.
Okay, so this one is ADC. Why are we going to use the SDC, not ADD?
Because we have a carry.
Okay, because you have a carry. Okay, we just take a easy example. Okay, you're going to add 17 with 28. Okay, so you add, so this is a, what we call here, this is a SAR, and this is a tenth. Okay, the SAR here is what we call here for the SAR. Okay, so this, okay, so 7 plus 8 equal to 15. Okay, and then you have a carry from this digit to the 10th digit. Okay, so that's why we're going to use the ADC, okay, for the higher byte, because sometimes, okay, when you do the addition for the lower byte, it might produce a carry. Okay, so you need to what we call here, consider the carry in the higher byte addition. Okay, so that's why for the higher byte, we always use the ADC, while the lower byte only use the ADD instruction. Okay, next. Okay, before we do the ADD and ADC, what are you going to do to these numbers here? Because the ADD and ADC, okay, only can be performed between two registers. Okay, so how are you going to do to these numbers here? What are you going to do?
We separate the lower nipples.
Okay, so you need to load these numbers to general purpose register. Okay, since, okay, the output of the result, the output of the addition here, you're going to put to R20, R26 and R27. Okay, why not this value? Okay, the first number here, you put it to R27. And this number here, you put to R27. Okay, the lower byte you put to R26, and this one is R27. What about 96 and 12? Okay, so this one you load to any registers lah, as long as it is from R16 to R31. So this one, let's say I use the R20, and this is R21. Okay, so now I write down the program. Okay, first we're going to load this number 2762129 and 96 to the GPR, and then after that we do the addition process. Okay, so LDI R27 with OX27, and then LDI R26 with OX62. Okay, so this is the first 60-bit number. Okay, and then you load the second 60-bit number, which is LDI R21 OX12, and then LDI R20 OX96. Okay, so this is the second 60-bit number. And then after that, okay, you're going to add this number here. Okay, we're going to add the lower byte first, and then followed by the higher byte. So ADD, okay, since the result you're going to put inside R26. So ADD R26, okay, and then with what register? R20. Okay, make sure that you choose the correct registers lah. Okay, and then followed by ADC R27. Okay, because the result you're going to put in the R27, and then what the second register? R21. Okay, so this is the program to perform this addition of 60-bit numbers. Okay, any question?
No, doctor.
Okay, now we look at the another examples. Okay, so this one here, okay, you are going to write a program, okay, to add one 60-bit number with one 8-bit numbers. Okay, so you have 2917, and then you're going to add with 18. And it says that you're going to put the result in R25 and R24. So R24 and R25. Okay, so what are you going to do? Okay, again, okay, since this is a 60-bit number, so you need to divide this 60-bit number to lower byte and higher byte. Okay, you need to identify lah. Okay, which one is a lower byte and which number belong to high byte. Right? Next. So for this one here, okay, you have two solutions. Okay, two solutions to perform this addition. Okay, the first one is the shortest one, and the second one might be the longest one lah. All right, so let's look at the shortest one. Okay, the first solution. Okay, so since this is, okay, you see this value here, 18 is smaller than 63. Okay, why not we use the ADIW? Okay, add one word with a immediate data. Okay, if you recall back, okay, we have the ADIW. Where is my ADIW instruction? SPC, SPIW. Okay, this is ADIW. Okay, you see here, you're going to add immediate to a word and make sure that your K is between 0 to 63. Okay, but this one in decimal lah. Okay, the example here is hexadecimal numbers. Okay, so you need to convert the 18 and see whether it is between the range. Okay, if between the range, then you can use the ADIW. If this number here, okay, the immediate number is above the range, then you cannot use the ADIW. Okay, so 18 you convert to decimal, so this one actually equal to 4. Okay, which is below that 63. So you can use the ADIW. So what you're going to do, since now this one here you're going to store in R24 and R25. Okay, so what happened here is, so why not we put the 17 to R24, and this one we put it to R25. Okay, so that's why LDI R24, okay, you load with OX17, and then LDI R25, you load with OX19. Okay, then after that, by using the ADIW, so ADIW R25, R24, comma with this immediate value. So the immediate value is 0818. So this is the program that you need in order to perform this expression here. Okay, this is the first solution. Okay, the second solution, which is the longer one. Okay, you can use this, what we call here. Okay, we can use the ADD and ADC instruction. Okay, so this one ADD, and while this one is ADC. But if you're going to use this one here, okay, make sure this value you replace with 0. Okay, why? Because the ADC need to add between two registers and a carry. Okay, so you need to put 00 to another register. This is an R24, this is R25. So this is, you can put it to R16, and this 0 here, you put it in R17. Okay, so the solution here is, okay, load I R24 with OX17, and then load I R25 with OX19, and then load I R18 with 0x18 and clear. Okay, you can use the clear because we're going to clear the R17. Okay, so you can put the clear R17, or you can replace with LDI R17 with 0. Okay, it'll do the same thing. Okay, then after that, we add the lower byte. Okay, ADD R24 with R16. Sorry, this one is R16. Yeah. Okay, please change it to R16. Okay, and then ADC R25 with R17. 17. Okay, so this solution here also perform the same expression. Okay, but okay, this one here you need 6 line of instruction, while this one is only need 3 line of instruction. So this one is more efficient compared to this one. Okay, next we are going to see here. Okay, you're going to write a program to multiply 25 by 65. Okay, you have a 8-bit number. You're going to multiply 225 with 65. And after that, you're going to find out what is the answer after you multiply this 8-bit number. So what are you going to do? Okay, so for the multiplication, we have 3 instructions, which is MUL, MULS, and MULSU. Okay, since this one here, it's not saying that this is a signed number, so you can use the MUL. So we just assume the numbers here is unsigned numbers. Okay, so what you're going to do? Okay, you just load the numbers, okay, to a registers. Okay, so 25 and 65, you put it to register. So this is a R23, and this one you put it to R24. Okay, so load I R23 with OX25 and load I R24 with OX65. Okay, then after that, you use the MUL instruction, MUL R23, R24. Then you're going to find out what are the answer and where is the result will be placed. Okay, for every multiplication, okay, for every multiplication instruction, the result will be stored inside R01 and R0. Okay, so because this is a R1 or R0, so you know that this is a 16-bit number. Why? Because 8-bit multiplied by 8-bit, you will get 16-bit number. So then we need to have 2 register here, which is R1 and R0 to store the results. Okay, so since this is only the MUL is for unsigned number, so you can simply press the calculator. Okay, 25 multiply with, okay, press the calculator, 25 multiply with 65, so you will simply get the, okay, E99. So now we're going to identify which numbers will store to R0 and which number will be stored to R1. Okay, since this is a 16-bit number, we can divide it to lower byte and high byte. So this is a lower, this is high. 99 will store at R0, while 0E will be stored at R1. Okay, so this is for the multiplication. Okay, next we have another exercise for the multiplication. Okay, so this one here, okay, you need to look very clearly, very closely, okay, how the multiplication is performed, because this one here involves the signed and unsigned numbers. Okay, so you're going to write a program to multiply 2 numbers as below and given the answers. Okay, for the A, both numbers are unsigned number. Okay, so both numbers are unsigned number means that you have 2 numbers here, which is F7 multiply. Okay, you're going to multiply with 0, 2. Okay, since this one here, both are unsigned number. Okay, you can simply press the calculator and take the value, take the result. Okay, so F7 multiply with 0, 2, you will get 0, 1 EE. Okay, you will get 1 EE. Okay, so this is the result. Okay, so how to write a program? Okay, first you need to load this value to your GPR and 0, 2 to another GPR, and by using the MUL. Why MUL? Because this is a unsigned number. So by using the MUL, then you multiply them, and the result IEE will be stored inside what register? This IEE will be stored inside what register after you
R0.
okay
R0.
R1 and R0. Okay, so EE will be stored to R0 while 01 will be stored to R1. Okay, for the unsigned number, so it is straightforward lah. But okay, for the B, F7 and 02 both signed number. Okay, so F7 and 02 both are signed number. Okay, so this is a sign. So what you're going to do? Okay, previously we already learned how to determine how to get the magnitude for signed and unsigned number. Okay, so since this one here, okay, it says that both are signed numbers. So what you're going to do is you need to figure out whether this number here is a positive number or negative number. Okay, once you figure out the number is positive or negative, then after that you can multiply. Okay, so let's look at the F7. So F7, if you convert them to binary, so you will get 1, 1, 1, 1 and 0, 1, 1, 1. Okay, since this is a signed number, so what happened here is bit 7 here, okay, will show you either it is a positive number or negative. Okay, since the bit 7 here is 1, so you know that this is a negative number. So the question here is how to find out the magnitude or the value of this number. How to get the magnitude? What are you going to do?
7, 7. 7, 7. Minus 7, 7.
Is it minus 7, 7? No, you need to do the second complement. Okay, do second complement, then you will get the value. Okay, if you simply put the 7, 7, then it is wrong. Okay, so we just convert this to get the value. Okay, from left to the right. Okay, you find the first number 1. So this is the first number 1. You copy back the value, which is 1. And then what about the rest? Okay, the rest you just
Flip.
Invert them. Okay, so this is 0, 0, 1, 0, 0, 0, 0. Okay, so here, what is the value for this one here? Okay, we change to decimal lah. Okay, why we change to decimal? Because it's easier for us to do a multiplication. Okay, so this one here, if you change to decimal, you will get 9. Okay, but previously, we already identified that the bit 7 is 1, so this one is actually a negative 9. Okay, so F7 actually represent negative 9 in decimal number. Okay, what about 02? Okay, so for 02, okay, again, you change this number here to binary representation. So you will get 0, 0, 0, 0 and 0, 0, 1, 0. Okay, you check bit 7. Okay, since the bit 7 is 0, so you know that this is a positive number. Okay, so for the positive number, no need to get the second complement. Okay, you can simply take this value as a magnitude. So the value for 02 is actually a positive 2. Okay, so now what are you going to do? Okay, you press the calculator. Okay, negative 9 multiply with 2, you will get negative 18. Negative 18 convert to hexadecimal, you will get F, 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 E, E. Okay, so now we are going to identify, because the result will be stored inside the R1 and R0, is it? And this R1 is R0 only a 16-bit. So now we're going to identify which value that will be stored in R1 and R0. Okay, so this one here, you can divide them to byte. Okay, so you have a 4 byte here. This will be stored to R0 and FF will be stored to R1. What about this one? These two here, okay, you just discard the value. So we only focus on this part here. So R1 and R0 will store FF, EE. Okay, see here. Okay, so FF, EE. So what instruction that you're going to use? You're going to use the MULS. Why MULS? Because both F7 and 02 are signed numbers. So that's why we're going to use the MULS. Okay, any question? Any question, guys?
No, doctor.
Okay, if no question, then we go to the C. Okay, for the C, okay, what the C says that? Okay, it says that F7 is a sign, while 02 is unsigned number. Okay, so it's saying that F7 is a signed number, while 02 is unsigned number. Okay, so since the F7 is a signed number, so what you're going to do, again, we change it to the binary representation and identify bit 7 either is a positive number or negative number. If it is a negative number, so what you're going to do, you need to get the second complement to get the magnitude of that value or the magnitude of that numbers. Okay, so this is a 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay, for 7. So you identify here. Okay, so this one here, negative number. So what you're going to do a second complement. And when you do the second complement from right to the left, okay, find the first number 1, copy back the value, and the rest you just invert them. Okay, and then you get the positive 9. Okay, since previously we know that this is a negative, so you just put the negative 9. So this is a negative 9. Okay, sorry. All right, and then what about 02? So since 02 is an unsigned number, so you can simply write, okay, so change it to the decimal. So this is actually 2. Okay, because unsigned number, no need to change. Okay, no need to refer to bit 7 to see whether it's positive or negative. Because the unsigned number, the value always positive number. Okay, so you multiply them. 2 multiply with 9, minus 9, you will get answer is minus 18, which is you get the same answer. So what happened here? You identify which one will be stored to R1 and which number will be stored to R0. So FF go to R1, EE will be stored to R0. What about how to write the program? Okay, again, you're going to load this number here to the register. Once you load this number to register, then you're going to use the MULSU. Okay, and bear in mind that, okay, you need to make sure that the position of the register is correct lah. Okay, since R23, okay, you put the sign number to R23 and R unsigned number to R24. Okay, when you do the instruction, write the instruction MULSU. Okay, the first register must be the sign number, which is R23, and followed by U, unsigned number R24. If you put the MULSU, R24, and R23, so what happened here? The 02 will become your signed number, while F7 become your unsigned number, which is wrong lah, according to this examples. So any question up until here?
Excuse me, doctor.
Yeah.
So how did you get from minus 18? You get FFEH.
Okay. This one here, you can simply press the calculator. Okay, if you doesn't have the calculator, what you're going to do is, okay, 18, okay, you change to binary dahulu. Okay, you change to binary numbers. 1, 2, 4, 8, 16, 32, berapa lagi? 6, 4, and 1, 2, 8. Okay, 16 plus 2, 18. while the rest you put 0. Okay, and then what you're going to do? This is a positive 18. Okay, to get a minus 18, you need to do the second complement. Okay, from right to the left, find the first number one. Okay, so this is your first number one. So what you're going to do, you just copy back the whole number here. Okay, until you see the first number one. What about the rest? The rest you just invert in there. Okay, and then this one here, okay, you change them to what we call hexadecimal. So this is a 8421. 8 plus 2 is 12. 8 plus 2 is 10. Plus 4 is 14. 14 actually is E. Okay, so this is only for the R0. What about R1? Okay, for the R1, you simply put the FF. Why FF? Because this is a negative. Okay, just simply put the FF to get it a negative number. Okay, so you will get the same answer as the one that you press the calculator.
So if it's always negative, I will put FF.
Yeah, if the number is negative, okay, you need to put FF in front of this number here. If the number is positive, then you put 00 in front of this number.
Okay, doctor. Thank you.
Okay, welcome.
Doctor,
Yeah.
actually I had class after this, so if you don't mind me, can I exit this class?
Okay, so I think we stop here. And before that, I'm going to give you another assignment. Okay, so later I will give the assignment inside the WhatsApp group. Okay, so we have finished our module 5. And tomorrow we're going to start with module 6. Okay, thank you.
Okay, doctor. Can you share the attendance, please?
Okay.